Hello, let's start our second session on functional analysis. In this session, we will be discussing about quotient spaces in detail. So, in last session, we have defined what is meant by coset of a vector space. Suppose E, hereafter I will be using E for linear spaces. Most commonly, I will be using E. Let E be a linear space and E1 be its subspace. Then we have defined suppose X is an element of E, we have defined coset of X as X plus E1, which is set of all X plus Y, where Y varies over E1. This is our definition for a coset, and we have defined we have noted that two cosets, class X and class Y, are either disjoint or they are equal. Class X equal to class Y. So how can we prove this? Either they are disjoint or they are equal. So I am assuming that anyway, one thing is sure, two cosets are either disjoint or not disjoint. So I am taking class X intersection class Y is non-empty. So there is at least one element, say Z, in class X intersection class Y. And this means Z is in class X and Z is in class Y. If Z is in class X, we can say that Z is an element of class X implies we can express Z as X plus some X1, where this X1 is an element of E1. Similarly, Z element of class Y implies we can express Z as Y plus some Y1, where this Y1 is also an element of E1. Okay, then both of them are Z. So we can say that X plus X1 is same as Y plus Y1. And this implies X minus Y equal to Y1 minus X1. But this Y1 and X1 are elements of E1. Y1 and X1 are elements of E1. So Y1 minus X1 is in E1 since E1 is a subspace. So it is closed under scalar multiplication. So this means X minus Y is an element of E1. So class X intersection class Y not equal to phi implies X minus Y is an element of E1. Okay. Now I need to prove that class X is equal to class Y. For that I am taking one element from the class X and I will prove that it is contained in class Y, and similarly we can prove the reverse inclusion also. So suppose I am taking one say Z in class X. So as we told earlier, I can express Z as X plus X1 for X1 element of E1. Now I can write this Z as X minus Y plus Y plus X1. I am adding Y and subtracting Y. So actually there is no change. And this is same as Y plus X minus Y plus X1, because vector addition is commutative. Okay, now we have have already proved that class X equal to class Y implies X minus Y is in E1. So this is in E1, X1 is in E1, so their product is in E1. So I can express Z as Y plus some element of E1. Some element of E1. So this Z is in Y plus E1, which is class of Y. So class of X is a subset of class of Y. If you interchange the roles of X and Y in this proof, we can prove that class Y is contained in class X also. So two cosets class X and class Y are either identical or they are disjoint. Class X intersection class Y is equal to 5. Okay. Now we have defined coset and we are defining quotient space now. Say here I will use E over E1. This is set of all class X where X varies over E. And we have already discussed in the last session that we can define a vector addition and a scalar multiplication here such that class X plus class Y is equal to class of X plus Y, and a scalar C times class X is equal to class of Cx. With respect to these operations, E over E1 becomes a linear space, and class of 0 is nothing but E1 will serve as identity. This is our 0 vector of E over E1. Okay. Since E over E1 is a vector space, it will have a dimension. So dimension of E over E1 is known as codimension of E1. Now let's do this problem. Find codimension of C0 in C. So we know that C means the space of all convergent sequences, and C0 means the space of all sequences that converges to 0. So surely this C0 is contained in C. So C0 is a subspace of C. So we can think about C over C0, and we have to find the dimension of C over C0. For that, I am taking an X from C. Means this X is a convergent sequence. If it is a convergent sequence, it will have a limit, and I am calling this limit as A. Okay. Now think about the sequence A, etc., the constant sequence A. Let me denote it by, say, Y. So Y is constant sequence A, etc. I can denote, I can express this as A times sequence 1, 1, 1, 1, etc. Let me denote this 1, 1, 1, 1, etc. constant sequence 1 as a big one. Now what about X minus Y? We know that X converges to A. Y also converges to A. That means X minus Y converges to 0, because both X and Y converges to A. So X minus Y converges to 0, and this means X minus Y is in C0. If X minus Y is in C0, we know that class of X is same as class of Y. Now this class of Y means, so I can from here I can write Y as A times big 1, where big 1 is the constant sequence 1. So this is class of A times 1, which is A times class of 1. So you take any class X. If you take any X from C, class X can be written as a scalar multiple of class 1. So we need only one element, one vector to span C over C0. Then we can say that dimension of C over C0 is equal to 1, because we need only one vector to span the entire space. So codimension of C over C0 is codimension of C0 in C is 1. In the next class, we will continue our discussion on quotient space. So go through these portions carefully and study well. All the best.